Thanks, Rana. I should say thanks to Alan Weinstein and the 40-metre team for having me. I've enjoyed my stay so far. And I would like to mention my thesis advisors, that's Mal Gray, Pinkoy Lamb and David McClelland, and also a couple of the postdocs that I worked with, Stefan Gosler, Ben Buchler, and a fellow grad student, Nikolai Gross. The work that I'll be presenting is our work mostly today, and we work closely with the squeezing group at MIT and also at Caltech, and also at University of Hanover. So I'm going to talk today about quantum noise and squeezing. I'm going to give a quick introduction and then talk about quantum noise in ground-based gravitational wave detection. Of course, quantum noise also limits space-based detectors by shot noise, but squeezing can't really help due to the large losses. A lot of my talk I'll be talking about how we developed low-frequency squeezing and my experiment at ANU, which is often termed crystal squeezing now. We use a nonlinear optic process, CaJAGWR medium, and there's similar projects going on at Hanover and also at MIT. And I'll briefly mention the MIT ponderomotive squeezing experiment as well. And then go on to the next step, which is demonstrating this squeezing enhanced interferometers. And there's been a couple of benchtop experiments at ANU and at Hanover, and also at the moment there's an ongoing experiment, or beginning experiment I guess, at Caltech 40-metre. So the motivation for squeezing or quantum non-demolition techniques comes from the fact that these are sensitivity curves of sort of current gravitational wave detectors. This is GEO, LIGO, and Virgo, and the lower trace is predicted advanced LIGO sensitivity curve as a function of frequency. And quantum noise is a limit over significant portions of this band for all these detectors. So for GEO, shot noise is this portion here. For LIGO, shot noise is this portion, and Virgo is similarly. For advanced LIGO, it's expected to be limited by shot noise, which is quantum phase noise, and radiation pressure noise, which is quantum amplitude noise. Over these sort of bands, an intermediate should be limited by another noise source, which is internal test mass noise. So a long time ago, Caves proposed that squeezing could reduce the quantum noise. And so this is just one of the many quantum non-demolition techniques that you can use, and the one I'll be talking about today. So that we can all start on the same page, I want to give some quantum optics introduction. So if we parallel the classical electromagnetic field and the quantum optics representation of the electromagnetic field, I can give you sort of some idea of, I guess, the quantum optics picture and so on. And so the electric field has an amplitude and phase. We know this, and the power can be easily written down, and we measure the power quite easily, and it's just the square of the electromagnetic field. In the quantum optics representation, we use the annihilation and creation operators, and similarly the power can be written down fairly straightforwardly, where we have h bar omega, the energy per photon, multiplied by A dagger A, where A dagger A is gives you the number of photons per second. So these are fairly sort of similar type equations here. The thing with A dagger and annihilation and creation operators is that they're not Hermitian, and so they're not observables. We can readily define Hermitian operators for the amplitude and phase quadratures, and these are done like so. And these operators satisfy the Heisenberg uncertainty principle. And so the Heisenberg uncertainty principle limits the precision that one can make simultaneous measurements of non-commuting observables. And so for the amplitude and phase quadrature, we write down the standard deviation of the amplitude quadrature, standard deviation of the phase quadrature, and this has some minimum value. So one more sort of set of slides with some equations, and then we'll get back to some phasor diagrams. So we can now separate these annihilation and creation operators into average and fluctuating terms. And we can write this fluctuating term in terms of the fluctuations in the amplitude quadrature and fluctuations in the phase quadrature. So the point of this introduction was to get to the stage where if we have a look at the phasor representation of the electromagnetic field now, we have the amplitude is given by the amplitude of the electric field is given by the length of this stick, and the phase is just given by the angle, where we have the axes are the real and the imaginary parts of the electric field. In the quantum optics picture, we have to consider that this electric field also has some uncertainty in both the phase quadrature and in the amplitude quadrature. And this is just a result of the Heisenberg uncertainty principle. And so this state would be called a coherent state if this is a minimum uncertainty state. And so it satisfies this relation here. And when we're talking about experiments, a coherent state is well represented by a short noise limited laser. So this is what a short noise limited laser source would look like in this representation. We're going to go through a couple more states here, a couple of important states. This one is the vacuum state. And this state is similar to the coherent state, however it has no coherent amplitude. And the vacuum state is particularly important because it exists everywhere, and it turns out that it's the source of quantum noise in gravitational wave detection. You can see it has fluctuations in the amplitude quadrature and in the phase quadrature. So what can we do about this? Well, we can define some other states which satisfy the Heisenberg uncertainty principle. Well, this is called an amplitude squeeze state, where you can see that the amplitude of this field has some fluctuation still. However, they're smaller than the minimum, smaller than the coherent state level, at the expense of larger fluctuations in the phase quadrature. A phase squeeze state would look more like this, where you have less fluctuation in the phase and larger fluctuations in the amplitude. So you could tell the phase of this particular state fairly accurately, however the amplitude would be fairly uncertain. And of course you can squeeze any angle you like. This is at 45 degrees, so you have large fluctuations in both the amplitude and the phase quadrature. However, at some intermediate quadrature, you have less fluctuations. Another important state is the squeeze vacuum state, where it's really hard to define quadratures now because you have no coherent amplitude to define your phase and amplitude, so you just have a squeezed and an anti-squeeze state we call quadrature. So these squeeze states can be generated, and what you require to generate one of these is a nonlinear process. And I'll be talking about two examples today: ponderomotive squeezing, which actually goes on in the LIGO type interferometers and advanced LIGO, and another technique which we use is using the chi2 nonlinearity of some crystals. So let me get on to the first one of the ways we can generate squeeze states, and that's ponderomotive squeezing. So what we have here is just some field coming in and reflecting off this mirror, and this field imparts a momentum shift, imparts momentum on the mirror, and the force is equal to the twice the power divided by the speed of light. And via the mechanical susceptibility, this mirror will move around due to this force. So this is radiation pressure. And the output field will have a phase shift. And this phase shift is proportional to how much this mirror has been moved around, so how much the displacement of the mirror. In this phase of representation, we can have a look at an input state. Say it's a coherent state. If of some amplitude like so, if it's of this amplitude, you may get some phase shift on the output state of about this size, say. If, yeah, exactly. No, I just mean that if you give it a force, then it will move. Yeah. And if you give it a larger force, it will move further and you'll get a larger phase shift. And similarly, if you give it less of a force, so if at one point if your field fluctuates to a low power, then the output field will have a less of a phase shift, and so you get this sort of transformation. So if you have high power, you have a larger phase shift, and you can see that this you can create some sort of correlations in the amplitude and phase quadrature. In fact, if you look at just the fluctuations for a moment, if the input is of minimum uncertainty, the output also has minimum uncertainty in the amplitude quadrature, because you haven't changed any loss of or anything to the amplitude quadrature. You've just added some phase shift due to amplitude fluctuations. So you have larger fluctuations in your phase quadrature. And this is, of course, radiation pressure noise in gravitational wave detectors. But you can see that if you look at some intermediate phase angle, you can see that there will be some squeezing. So the second nonlinear process.
So you're saying that after the Ponderosa squeezing, you're no longer in a minimum uncertainty state?
No, it can be a minimum uncertainty state.
You can maintain even though I thought what you just said is that the amplitude quadrature is unchanged, but the phase quadrature is now spread out.
That's what I said. But the extra phase shift you have is correlated to the amplitude quadrature.
So that maintains the coherence.
Yeah.
That maintains the minimum uncertainty.
That's right. So if you look somewhere in between the amplitude and phase quadrature, you'll see that, yeah, these correlations. And so now you do have an anti-squeeze quadrature and a squeeze quadrature, but yeah, it's the product of the two can still be 1 if you have no loss. So the other technique was to squeeze a field, or one other technique, is to use nonlinear media like CaJAGWR nonlinear media. And I'm going to talk mostly about the optical parametric amplification today. And so this is related closely to second harmonic generation, which is used in a lot of lasers that we have these days. Laser pointers, a lot of green laser pointers are doubled, that sort of thing. And the process is simply described here in terms of these waves here. Of course, sorry about having to describe these as waves. Of course, they're particles. And so these two photons here interact in this nonlinear medium and can be converted into one outgoing photon at twice the frequency. And so in our lab, at least, we have, this is 1064 nanometers, and we can produce 532 nanometers. And the complementary process is optical parametric amplification, where you have the two fields entering at 2 omega and at omega, and you can have amplification of your field omega at the output here, and so you destroy your 2 omega field and create 2 omega fields here. And it turns out you can actually de-amplify this input field as well, depending on the phase relation, and I'll talk slightly more about that in a second. Another process that is allowed to happen is that if your 2 omega field is strong enough, you don't actually have to, I'll say, seed this process. You can just have vacuum fluctuations, and you can get down conversion into 2 omega fields here. And this is a nonlinear crystal. This is lithium niobate. It's 2 millimeters by 2.5 millimeters by 7 millimeters long. And for this process to occur, we temperature control this crystal. And that's why it's sitting on this. This is a Peltier element here, and there's a lid that sits on top.
Is that really the third picture? Put in few watts of green light. How much do you get that?
So it can be a lossless process, ideally. These nonlinear processes, if there wasn't any linear absorption, it can be 100% efficient. The typical sort of efficiencies you get for second harmonic generation can be 70% you can buy commercial SHGs, or 90% you can get them up to. And I think you can get similar sort of things with OPO. So this OPO, optical parametric oscillation case, only occurs when you have enough 2 omega fields. So you can put in a fairly substantial amount of 2 omega and effectively no coherent photons come out. So I previously mentioned the relative phase of these two input field matters determines whether you get amplification or de-amplification of this output field, of this field here. On a phasor diagram, it looks like this. You have these, again, amplitude and phase quadratures. If you put in an input field in the infrared, like so, and its phase relation is in quadrature to the pump field, what you get is an amplification of the DC stick, and also of the ball, and you get some squeezing. And so this would be a phase squeeze state. If you change the phase relation of those two input fields, then what you get is some de-amplification, and this would be an amplitude squeeze state. So this is a schematic of what an experiment would look like. If we had a laser of 1064 nanometers, we would send a lot of this light to go to the SHG to create our pump, our 532 nanometers, and we could combine these two fields on this dichroic beam splitter here and put this into an optical cavity. This is our nonlinear medium. We use an optical cavity to enhance the nonlinearity, and what you can get out is you can get out a bright squeeze state, and so this is what that would look like. So this would be a de-amplified state. However, if you simply place a beam dump here, there's no longer any power entering in at 1064 nanometers. It's actually only vacuum state. What you get out is called a vacuum squeeze state, and so this is quite often how we operate, and it's called below threshold optical parametric oscillator, and leads to a vacuum squeeze state. Possibly interestingly enough, the amount of squeezing, there are actually some photons in here when we say vacuum squeeze state. It's not quite the truth. The amount of photons you have is proportional to how the amplitude of the squeezing. And for a 10 dB squeeze state, so if you de-amplify the quantum noise by a factor of 10, you have about 2 photons per bandwidth, so per second. So that would be for a megahertz line width cavity, you'd be producing 2 million photons per second. So what determines this phase? Well, you can. This phase is. It seems fairly arbitrary because there's no coherent stick or no coherent power, but you can change the phase by changing the pump field phase. So if you had like a phase shifter in here, like a piezoelectric transducer on a mirror or a phase modulator, you can change the phase of the output squeezing. Or at the output, you could just change it here, if you just gave an extra path length, I guess. So now I want to talk about the quantum noise in gravitational wave detectors. And I'll start by saying that the quantum noise is not due to the test mass quantization of the mirrors. The quantum noise is due to our measurement device, which is light in interferometric gravitational wave detectors. The picture that Caves pioneered a long time ago was that it was the vacuum state in the dark port that is responsible for our quantum noise. And so let's just take a minute and try to work out why this is so. So we lock our Michelson interferometer to a dark fringe, which means that all of the input light comes in from the laser, is split, goes down the respective arm cavities, and interferes constructively back towards the laser. So any of the power goes back towards here. Also, any of the laser fluctuations, classical, quantum, also end up back towards the laser. This device effectively acts like a 100% mirror in the case of no loss. So if you look at it from the photodetector's point of view, the Michelson also looks like a 100% mirror. So whatever field would come into the unused port is split and then recombined and constructively interferes towards the photodetector port and destructively towards the laser. And so if we have a vacuum state, well, we will always have a vacuum state. The Heisenberg uncertainty principle says that we must have one. So it effectively gets some phase shift and reflects back off to the photodetector. So if we have any gravitational wave signal coming out, we'll also have some uncertainty imposed on it. And so I just wanted to mention for our Michelson interferometer, the quantum noise is a sum of the shot noise, which looks like this for advanced type detector, without signal recycling, and radiation pressure noise, which has this frequency dependence. So shot noise can be reduced by increasing the power. So shot noise is proportional to the square root of the power at the beam splitter. And so you can just keep on reducing your shot noise by increasing the power. But by the way, this shot noise is actually flat. The dependence here comes from the fact that the arm cavities become less sensitive at higher frequencies outside the cavity line width. So whereas radiation pressure noise is really a competing noise, this is due to the amplitude-dependent phase shift that I previously mentioned, and has a frequency dependence due to the response of the test mass. So it's given by this slope due to the fact that the mass acts like a free mass. And this is proportional to the square root of the power. So as you increase the laser power, this line increases. So let's try and understand these noise sources in terms of the ball and stick diagram again. So this is our input state. This is the vacuum state. And this is our output state. So like I said before, the output is equal to the input fluctuations multiplied by some phase shift due to the fact it's propagated. And in the phase quadrature, there may be some signal, perhaps from a gravitational wave. And so at the output, you measure the phase quadrature, and so you have your signal here. And superimposed here is your vacuum state with fluctuations in the amplitude quadrature, which are unimportant, but the fluctuations in the phase quadrature are important. And so this is the case for your short noise limited regime here. In the radiation pressure noise limited band, it's slightly more complicated. So in the output relations, you have the same terms again. So in the output of the amplitude quadrature, you have just whatever came in plus a phase shift. But in the phase quadrature, you have the phase fluctuations that came in plus some radiation pressure coupling term times by the amplitude quadrature fluctuations. So this is the momentum kicks on the mirrors here. And these have some phase shift plus your gravitational wave signal. And so you can see that in the radiation pressure noise limited regime, you have extra phase fluctuations due to this, due to the amplitude fluctuations that move your mirrors. So what happens when you put it in a squeeze state? So this is just the case that I just showed you in the shot noise limited regime in this upper diagram, and the radiation pressure noise limited regime in the lower diagram. So shot noise limited and radiation pressure noise limited. This line here, by the way, you can't read it, but it's the standard quantum limit. And so if you put in a phase squeezing, you can see in the shot noise limited regime, your signal to noise improves because you're only interested in the phase noise. Whereas in the radiation pressure noise limited regime, because there's extra amplitude fluctuations, you have extra amplitude induced phase fluctuations, and so you do worse off here and improve the shot noise limited sensitivity. If you put in an amplitude squeeze state, you can do a similar type of thing, but you do worse off in the phase noise limit in the shot noise limited regime, and better off in the amplitude noise limited regime. And you can put squeeze states in also at 45 degrees, for example, and you do better where radiation pressure and shot noise are equal, and worse everywhere else. If you're fairly clever, you might be able to produce a squeeze state which has frequency dependence. So you have amplitude squeezing at low frequencies, some optimal rotation in the intermediate frequencies, and phase squeezing at high frequencies. And so this is allowed. Now, advanced LIGO is going to have signal recycling, as does GEO at the moment, and so it's interesting to know how squeezing interacts with signal recycling. So signal recycling interferometers, this is a sensitivity curve from advanced LIGO for the quantum noise limited band, and this is the SQL again. It looks perhaps a little bit like internal thermal noise, but it's not. You can see that the sensitivity of advanced LIGO already beats the standard quantum limit. And this is because the signal recycling mirror reflects back back the radiation pressure, so the squeeze state that the interferometer generates, and you can get some correlations which allow you to already do better than the standard quantum limit. These are a couple of traces that I put in which, if you put in frequency independent squeezing, you can improve the sensitivity over some band and reduce it everywhere else, or you can do if you put in the squeezing at a different angle, you can get this green curve, and this pink curve represents if you had frequency dependent squeeze, which is no easy task, but it is possible. So I'm going to talk about now the development of getting these squeeze states at low frequencies. And so what does one want, what does one require if you want to inject squeezing into gravitational wave detectors? Well, you require squeezing at the same frequency as the gravitational wave signal. So this is the audio band for ground-based detectors, 10 Hertz to 10 kilohertz. And like with all things, more is better, so you want to have more squeezing, which will give you better sensitivity, better noise reduction. You need to be able to control the phase of the squeeze state, and it's ideal to have frequency-dependent squeezing at low frequencies. So what's the problem with producing squeezing at low frequencies? Well, you might ask, I guess squeezing's been around for over 20 years now. The problem at low frequencies comes about because you have noise sources where you wouldn't in the megahertz. So typically squeezing is produced in the megahertz where your lasers are shot noise limited and you can already be at the quantum noise limit. And so you just have to reduce the quantum noise limit from there. At low frequencies you might have large classical phase fluctuations and amplitude fluctuations. So these are sources of noise that you have to somehow overcome to get to the quantum noise limit and then squeeze below. The other question you might have is, why can't we measure large amounts of squeezing, like 10 dB of squeezing? And the reason is, in a nutshell, any loss mechanism couples in the vacuum state. So to produce, say, 10 dB of squeezing, you need to have, from generation to detection, the loss must be less than 10%. And given that the standard photodetectors have a loss of 10%, it's quite a hard task to have no other loss in the system. So to produce low frequency squeezing, we have two options. We can either reduce the noise sources, so we can reduce the laser classical and intensity and phase noise, so we can have pre-stabilized laser, and all these other noise sources like acoustic noise and that sort of thing, which it can be quite tricky in a laboratory environment. Or you can reduce the coupling of these noise sources. And it turns out that if you produce vacuum squeezing, then you can effectively do this second one fairly simply. So this slide is to show you that vacuum squeezing is inherently immune to these classical noise sources. And this equation will probably mean nothing to you, so maybe I can walk you through it. The squeezing that you get at the output has a dependence on what the field fluctuations are on the input. So if you have fluctuations in your seed field, this is this variance here, and some coupling coefficient. Any loss couples in the vacuum. If the pump field has classical amplitude and phase fluctuations, and also if your cavity has some detuning fluctuations, you get this term here. These last two fields here, the pump fluctuations and the detuning fluctuations, are scaled by n, which is the intracavity photon number at the fundamental field. So I can easily reduce that n here by blocking the seed power in here and just have vacuum seeding. And if I work below threshold, this n equals 0. And what you get out is a squeezed vacuum state. This n goes to 0. These two terms no longer couple, and the variance of the seed is just the vacuum field. So we come up with a statement that below threshold OPO is immune to laser noise, pump noise, and detuning noise. And so we did an experiment to verify this This is a schematic of the experiment. We just have a CaJAGWR laser, 1064, which is frequency doubled, and this is our OPO cavity here, and we have some of the laser comes in here for the seed of the OPA, and some of it's reflected, and we set up a homodyne detection system. So we just interfere whatever comes out of the OPA cavity on this homodyne detection system. The other thing here is a VA, which is variable attenuator, and we simply attenuate the input field power, and we have a look at how the squeezing develops over as we change this variable attenuation. And I should mention a couple of things. This cavity was not electronically locked. We just held on resonance by hand because when we previously set up this experiment to lock the cavity using pound-driven Hall lock-in with the seed power. But if we were reducing this to 0, then we could no longer use that as a phase reference. And the other thing I should mention is that once we produce a squeeze state here, we can lock the phase of the local oscillator and the squeeze state by looking at the squeezed and the anti-squeezed quadratures as a phase reference. So generally, you'd use phase modulation and lock the phase modulation of a coherent field and lock using that technique. But we use we phase modulate the relative phase of the vacuum field in the local oscillator and lock using that as a phase reference. And so this is a spectrum relative to the shot noise limit. So this is the shot noise limit here, and it's a spectrum from 3 kilohertz to 100 kilohertz. And this spectrum was taken with a seed power of 6 microwatts. And we changed no other experimental parameters except for the seed power. And what we found was that as we lowered the seed power, we would recover more and more squeezing across wider and wider band. And so until at very low seed powers, we recovered audio frequency squeezing. And so this was a fairly good realization, a fairly simple realization that allowed us to squeeze it across the gravitational wave detection band. And
What was all that before?
It's quite likely. So I think there's all these features here, and laser noise is one of them. I think this particular feature we tracked down to being some amplification, some noise amplification in the SHG cavity. So the SHG cavity was somewhat unstable at this particular frequency and produced some intensity noise, and that was coupling into our squeeze beam. And I guess maybe over all the rest of this audio band, if you go low in frequency into a few hundred hertz, we saw mechanical resonance of mounts, optics, and all that sort of thing. I don't know what this one was.
So the big spike that's remaining is your control signal?
That's exactly right, yeah. So to control this, we dithered one arm of the homodyne detector, and that's at this frequency here.
Is that very stable? A stable way to control phase? Or?
It turns out that it is stable, and I'll show you a plot where we lock the whole system for 15 minutes or so. We've been able to lock it for slightly longer, but we always seem to run out of range of our PZTs. But it seems you can get a large amount of squeezing locked for a relatively long amount of time. I think it's probably not the type of locking you'd want to use for a gravitational wave detector. You'd probably like to have a coherent lock-in signal like a phase modulated beam, which is offsetting frequency or something. So from this initial proof of principle, we went on to design another squeezer, a vacuum squeezer that has length control, and we wanted to get more squeezing, I guess, with the two key goals. And so we produced a bow tie cavity with our nonlinear crystal just here. And so this cavity was different from our previous one because we had it was doubly resonant, so it was resonant at both the pump frequency and also at the seed frequency, so at both red and green. And this allowed us to use the pump as a phase reference, so we could control the cavity length using the pump field, and we could just produce squeeze vacuum continuously. Another couple of features was that we went from a standing wave cavity to a travelling wave cavity, and this gave us extra isolation from backscatter and that sort of thing, which was spuriously seeded in our cavity previously. And we used a new type of crystal. It's called PPKTP, basically, and it has a high nonlinearity and is phase matched at body temperature. And so this is what the experiment looks like on the bench top. This is the PPKTP crystal. It's 1 millimeter high, 2 millimeters wide, and 1 centimeter long. This is what the bow tie cavity looked like before we put the crystal in the cavity. And you can see this is Rayleigh scattering. It's a fair amount of it. And so this whole experiment fits on about half the size of a large optical bench. We have the key components are our laser, our second harmonic generator. The pump power comes winding through here into our OPO cavity here. And we do some control of the OPO cavity. And the squeeze field comes out here and is measured on our 2 photodetectors here on our homodine detector. For our homodine detector, we have this tap off here, which is filtered through a mode cleaner and locked to the squeeze state. So this is what the squeezing that we got out looks like. This is at 100 kilohertz. This red trace is the short noise limit. And if you scan your squeezing, you essentially measure the projection of your squeezing ellipse. So you have anti-squeezing and squeezing and anti-squeezing and squeezing. And we're also able to...
Scanning your PCT of some length?
Yeah, exactly.
This is up downstream of the OPO towards the homodine detector?
Yeah, it's in the homodine detector. We just scan the path length of the local oscillator, which puts a relative phase shift between the squeeze vacuum. And so this is over half a second. And you can see this is the amount of noise we measure at where you encounter the squeeze part of the ellipse, you have noise suppression. And this is around 5.5 dB of noise suppression, which is close to the maximum measured at 1064. And so you might ask why we have a larger amount of noise in our anti-squeeze quadrature. So this is like 14 or 15 dB, and only 5, maybe 6 dB squeezed. And the reason is because we couple in extra vacuum noise. So we couple in loss, and the loss, whenever you have any loss, it moves your state closer and closer to the vacuum state, and so it turns out your squeezing quadrature is affected much more than your anti-squeezing quadrature, I guess. And so we have a total loss of 17%. So if one was to use this particular squeezer to inject squeezing into, say, LIGO, you start off with around 8.2 dB of squeezing coming out of the squeezer. And you know that because you know the loss of your photodetectors, of the interference efficiency with your local oscillator, and some losses on optics.
So you said the losses affect your anti-squeezing more than the squeezing.
Did I say that? I think it's the other way around. The losses affect your squeezing.
You're right, okay. But is it sort of one man's squeezing, another man's anti-squeezing? Does it depend on the quadrature you're interested in?
So you know which quadrature it is relative to the shot noise. So the reason it affects the squeezing quadrature more than the anti-squeezing is because you know this is 1 unit of quantum noise here, and if you had perfect squeezing, so you would have no loss, we would get down to around 0.1. So we would have 10 dB of squeezing or so. We'd get 0.1 units of quantum noise. And if you now add half a unit of quantum noise, then you get 0.6 relative to quantum noise, so you'd only get 2 dB of squeezing. Whereas if you take away, so if you have, in the anti-squeeze quadrature, if you have, say, 10 dB of anti-squeezing, so that's 10 times the shot noise limit. If you get rid of half of that, you have 5 plus an extra half. You still have a fairly large value above shot noise. So sorry if that was slightly confusing, my explanation, but it makes sense that if you have a lower noise source, if you add a noise source to it, it affects the lower noise source more than the upper noise source, right? So if we lock our squeezing and measure the spectra, this is 10 hertz to 100 kilohertz. This is our homodyne trace, which is shot noise limited at these frequencies until about 1 kilohertz, where you can see that it sort of starts to roll up, so it's no longer shot noise limited anymore. You can see the noise suppression we have by, if we lock our squeezing, this is the noise suppression we have, around 5.5 dB of squeezing, and this too rolls up at low frequencies. And if you extrapolate a line across your shot noise from here, we have squeezing to around about 40 hertz or so. And so the reason I think that we don't have squeezing at 10 hertz, we don't have this same level of squeezing all the way down to 10 hertz, is because our homodyne detector is not shot noise limited. So there's some extra noise source which combines with shot noise that makes this roll up. And this same noise source adds to the squeezing, and it affects it more because it's a smaller signal. So, like I said before, you can use this quantum noise lock-in to lock your system fairly stably. This is measured at 100 kilohertz, and this is the noise suppression below the shot noise limit that we measure, and this is over 15 minutes or 14 minutes. And so we have an average of 5 dB measured over this time. So stability is not what you'd want to inject it into an interferometer just yet, but it's really not that far away either. So I should mention that there's other projects that are doing fairly similar work. This one's this particular trace, which is squeezing this red curve as a function of frequency again. So this is the Hanover result. They have squeezing all the way to 10 hertz. They too have this roll up here, but this is just an artifact of their electronics. And so they have, yes, squeezing all the way down to 10 hertz. And they don't use noise lock-in, they have a coherent lock-in technique. They use a offset laser by they inject a second laser which is phase locked and offsetting frequency, and they can control their squeeze state by using this second laser. And
presumably this roll-up at low frequencies it's not quantum noise, it's another kind of noise.
It's another noise source. So.
Okay. So if you squeeze the quantum noise, it has no effect on the other noise, and if the other noise dominates, why do you still see squeezing?
So for these guys, this roll-up is an artifact. This is actually shot noise. For us, it's different. It's.
Oh, okay. For them, that's really quantum noise limited all the way down.
That's right. They go to some effort to show that. For us, it's different. You can see that the gap between these two traces actually decreases at lower frequencies, like you would expect. I was also going to say that MIT, and now because Kazuki Goda's here, Caltech have a similar sort of squeezer where they have shot noise and squeezing over a similar sort of band. So this is another type of squeezing. This is Nergus Mavalvula's group and Thomas Corbett at MIT. They generate, they're trying to generate ponderomotive squeezing. This is a fairly exciting experiment. They have a pre-stabilized laser which they inject into a Michelson interferometer, which is sort of folded, and so the paths have these arm cavities in them, which are fairly high finesse, and these end mirrors are quite light. They're 1 gram end mirrors, and so the idea is to produce ponderomotive squeezing and extract it out the dark port. These guys, it sounds like a very difficult task because because it's hard to produce squeezing when all your other displacement noise is a problem, and it certainly is. They use a couple of tricks, however. They use the optical rigidity, so they detune these arm cavities and use the optical spring effect to reduce the displacement noise. And these guys expect to measure around 5 dB of squeezing at below 1 kilohertz. So in the summary of the low frequency squeezing is that we have squeezing across the gravitational wave section band. We have a reasonably large amplitude of squeezing, and we can lock it. What we don't have at the moment is frequency dependent squeezing at low frequencies. However, this is not critical. So
Sorry. So the locking, noise locking works, and if you're squeezing coherent light, it works. But squeezing the vacuum, the only way you know of doing it is noise locking.
no. So the Hanover group, and also I think Go's done this as well, have used a second laser, and they've offset this in frequency.
Right.
And what you can do is, so at the main laser frequency, you can have squeezed vacuum, but effectively you can put another laser field at a different frequency onto that squeezed vacuum, and you can use it as your phase reference. So from the main laser frequency point of view, you have a squeezed vacuum, but you also have this bright sideband that you can use.
Right. So Go's working on that, but hasn't quite succeeded. Has anyone succeeded?
So yeah, the Hanover group, yeah, that's what they used.
So the noise locking, the better the squeezing, the better the noise locking gets. So when you're up to 10 dB squeezing, it's fine.
That's right, and the reason that is because you're using noise as your signal, and so you're using the quadrature asymmetry, and if you want to lock to the squeeze quadrature, which is intrinsically quieter, some significant amount quieter than your anti-squeeze quadrature, you get a better signal. And if you lock to your anti-squeeze quadrature, you get a much worse signal because it's intrinsically noisy.
If you have really bad squeezing, it doesn't matter if you're locking bad anyway.
That's true.
It's just a ball.
Yeah, if you have a vacuum state, you can lock it anyway. So once you have squeezing, you want to demonstrate some squeezing enhancement in interferometer configurations. And I'm going to mention a couple of configurations. This work's been done since 2000. I should mention that previously there's a couple of squeezing enhanced interferometers at Mark-Zehnder and a polarimeter done in the late 80s by, I think Kimball's group was one who did the Mark-Zehnder, and Grandier's group was one who did the polarimeter. So this is some work we did back in 2002 where the squeezing's at megahertz, and what we did was we built a power cycle Michelson interferometer on the benchtop, and we had a squeezer which operated at a few megahertz, and we injected this squeezing, this was bright squeezing, into the dark port of the interferometer, and combined the fields here and measured what came out of the photodetector. And we induced a signal on the differential mode of the power cycle Michelson to show our signal to noise. And these are the traces. So this top trace here, these blue and red, here is shot noise. And the difference between the red and the blue is that we had no power cycling mirror for this blue trace, and so our signal here was fairly small. Once we increase the power at the beam splitter, you get the power cycling enhancement of the signal. The shot noise was still the same. And then we injected squeezing, and we had reduction of the noise here. And so if you see this sort of aqua-coloured trace here, you can see that the signal is around the same size. However, we had suppression of the noise. So we showed...
and why is the signal not really the same size?
I guess because the signal that you measure here is a sum of the noise plus the actual signal. And so if you actually reduce the noise, you get the signal is slightly smaller. I mean, the signal is independent of the noise, right? But what you measure in a spectrum is the integrated signal plus noise. So if your integrated noise is lower, then the signal plus noise is slightly lower. Yeah. So the Hanover group have done a slightly more complicated version recently, where they use a dual recycled interferometer, so they have power and signal recycling. And the thing about signal recycling is you need frequency-dependent squeezing to get broadband improvement. So this is their noise trace. This is the black curve here is the shot noise. And you can see if you simply inject squeezing without this filter cavity here, and it goes in, combines with the interferometer light and comes back out to the photodetector, what you get is squeezing enhancement at frequencies not at frequencies away from the signal recycling resonance for them, which was at 10 megahertz. And at 10 megahertz, you actually get some rotation of the squeeze field, and so you get some degradation of the sensitivity. And so what they showed was that if they put in a filter cavity, which was detuned to the same frequency, but on the other side of the carrier, so detuned to minus 10 megahertz, they were able to, the phase shift of the filter cavity and the signal recycling cavity was able to phase shift both squeeze and sidebands, and you recover broadband squeezing improvement. So I'm going to finish off now by talking about CaJAGWR's work with the 40-meter team, and the idea here is to now introduce squeezing into a suspended interferometer, and the interferometer will have a realistic control scheme because it's a 40-meter and it's a prototype, and Go is fairly close to doing this. He has his squeezer built on the PSL table. He also uses PPKTP in a linear cavity, however, and he has good levels of squeezing and is really ready to inject the squeezing in the next month or two. So this is a fairly exciting time for squeezing. So I'll conclude now and say that because advanced detectors will be limited by quantum noise over a lot of the detection band, we can use squeezing, and squeezing is now a reality, and we're able to produce large amounts of squeezing. Ponderomotive squeezing is close, and squeezing is currently been injected into the 40-meter. So thank you for listening.